going to start just right back up with the rest of the reactions in chapter 9. Are there any questions before we start? Pretty dark in here with all these clouds. Okay. All right. Well, if there aren't any questions, we'll just go ahead and get going. I think what we'll do is sort of summarize where things are, and which hopefully will help you with keeping track of everything. So the first reaction that we spent time on was the hydrohalogenation. And in this reaction set, you had two. You had the HCl, HBr, and HI reactions to make the Markovnikov product. Okay. Then you had a second HBr in peroxide reaction, and I'm just writing hydrogen peroxide, but any peroxide should be fine. And this will give you the anti-Markovnikov product. The mechanism is in the first group. The second type of reaction that we looked at was the hydration. And there were three hydrations. The first is acid catalyzed. Okay. The second was the oxymercuration with a separate demercuration step. And the last was the hydroboration oxidation. And within these, you had Markovnikov addition here, Markovnikov here, anti-Markovnikov here. You had mechanisms for all of the three, or at least some details for all of the three. Let me move this over just a little bit. There are limitations for the acid catalyzed hydration. The limitations are the potential for rearrangement and the potential for the formation of a racemic mixture that you can avoid if you use the oxymercuration demercuration. Hydroboration, if you have a cyclic structure, you'll get a mixture of enantiomers as well. Hydrohalogenation can have carbocation rearrangements, but you can't do anything to avoid that. Okay. The third that we looked at is hydrogenation. And that is using hydrogen over some reactive metal, catalytic surface. And we used platinum, nickel, palladium. Sometimes they're on a carbon surface. There's no mechanism for this except that you should know it's syn addition, so that if you have a cyclic structure, the two hydrogens would come on the bottom, which would push the other, if there were other substituents on those vinylic carbons, they'd get pushed up. Okay. The fourth was halogenation, which is Cl2 or Br2. These add by anti-addition, and if it's cyclic, you're going to get a mixture of enantiomers. This one you had a mechanism for as well. Then we did halohydrin formation, which is the chlorine or the bromine, but it has to be done in water. Anti-addition as well. And you need to have a mechanism. So those are, we did a lot yesterday. So those are the ones we did yesterday. And we have really just 2 left to do. One is on the table in 9.1, and that's called the dihydroxylation. And then we'll come back, or you can go back and fill this in. There's 2 types of dihydroxylation. It just depends on whether you want to make a cis diol or a trans diol. A diol is a dialcohol, so you have to have 2 OH groups on your compound. And then the last thing that isn't on this table, but we are going to look at, is something called oxidative cleavage. Okay, and we'll come back to that. So that's where we are. We did 1 through 5 yesterday, and then we're going to do 6 and 7 today. I have some sort of summary problems, and we'll kind of have to take a vote on those, because they either are going to be, they're probably better review questions, like to look at and think about on Monday, but I don't mind doing a few to kind of give you a feel for how questions could be asked. So we'll talk about that, and you guys can vote or whatever once we get through the material. Are there any questions before we dive into dihydroxylation? Okay. All right, so this is section 9.9. Oops. Let's write it down a little bit. Okay. 9.9. Oh, let me see. Dihydroxylation. Okay, and the name is telling you what's happening. You're adding 2 hydroxides. Okay, so this is OH and OH. Okay, and the first one we're going to look at is going to function by anti-addition. Okay, but before we go too far, I want to actually I'll show you a reaction, and then I'll use some terminology. Okay, so I'm just going to show you the reaction and then point out the bits and pieces that you need to know. So here we have our substrate, cyclopentene, and this first step is going to use a compound. I want you to write RCO3H. Okay. Then what happens as the result of that first step is you make a compound in which the 2 carbons that had been in your alkene form a 3-membered ring with oxygen. In step 2, if you treat that 3-membered ring structure with acid, you make a trans diol. So these species, these diols, they actually have quite a few other names. You can call them just diols. You can call them 1,2-diols. You could call them 1,2-dialcohols. Or you can call them glycols. They all mean the same thing, that you have two hydroxide groups on adjacent carbons. This structure here, where you have this three-membered ring with the oxygen, this is called a epoxide. Okay. And it's a three-membered cyclic ether. So remember, ethers are ROR groups. So you just have the R's as the carbons in the ring. And because of the bonding and the size of an oxygen, you have to have them on the same, they have to have the same type of bond, dashes or wedges. Okay. This part from here to here, step 1, forms the epoxide, which is stable. Epoxides are stable. So you could isolate this and store it, and you will not form the diol unless you do step 2 as a separate chemical step. So you could stop here. This isn't like a carbocation where you have to do the second step because of instability. This is a stable structure, so you have to do this second step. If this was gone and all you had was RCO3H, all you would make is the epoxide. All right, now this RCO3H bit, okay. This is called a peroxy acid. Okay, now peroxides always have a structure that looks like this, an oxygen single bonded to an oxygen. Okay. Now the most commonly used one is MCPBA. Okay. And it's a peroxy acid, and its long name is metachloro. Peroxy, oh wait, I had that wrong. MCPBA, I had the letters in the wrong order. Metachloro peroxy benzoic acid. So if you look at what you have here, you have to have a chlorine, you have to have a peroxide, and you have to have a peroxide type benzoic acid. So the benzene part of this is a 6-membered ring. Then the peroxy acid part looks like this. Okay, so the peroxy acid is here. Now what the meta means, and this is more important in 212 than it is, but it's important for the structure. Meta is telling you a position of 2 groups bonded to a benzene ring. So right next door to the carbon with the peroxy acid, this position is called ortho. This position is called meta, so that's where the chlorine is, excuse me. And this one that's across is called para. So ortho, meta, para. So because the chlorine is in the meta position relative to the benzoic acid, that's why you have that bit in there. But usually it's just shortcut written MCPBA. In terms of mechanism, this first step, you're going to have no mechanism. The second step, you do have a mechanism. Okay. All right, are there questions before I erase the bottom part of this and then show you the mechanism for the second step. And erase the bottom. Okay. So we're going to start with this structure. Oops. And we need a hydronium cation. Oops. Okay. And what we're going to have is a proton transfer. Oxygen takes the proton. These sigma electrons go onto the oxygen. So you form this species. You still have your epoxide, but now it's protonated. So the oxygen is being forced to carry a positive charge. So it's pulling on electrons in the bond. These two from the hydrogen, these two, and these two from the wedge bonds. Okay. Now I'm going to show from the bottom. So can't attack from the top because it's blocked with this protonated epoxide. I'm going to attack the bottom and then move those sigma bond electrons over to that oxygen, which will make this oxygen hydroxide on a dash or wedge bond, excuse me, up here. Okay. This carbon now has a protonated alcohol group, which you can deprotonate with other water molecules that are in your reaction. Hydroxide up, hydroxide down. Okay. And then depending on if I had attacked the top carbon instead of the bottom carbon, I would have gotten the enantiomer. Okay. So you're going to end up with a racemic mixture. Okay, are there questions about the ring opening for that cyclic ether? Okay, I'm going to erase this and we'll do the syn addition. It's still a dihydroxylation, but now they're going to add to the same phase. Syn addition. Okay. So in this, there's no mechanism here for this in either of the steps. This time what we'll do is we'll use a cyclohexene. And what you treat it with is called osmium tetroxide. And And what you make is a very messy structure. Osmium is a metal. Metals do all sorts of weird stuff. They don't follow 8 electron rules. So this osmium has 14 electrons around it, which is not uncommon for metals. Metals don't follow an octet, they follow an 18 electron rule. This part is called a cyclic osmate ester. Okay. This is treated with a reducing agent, and you have a choice. You can use sodium sulfite in water, or you can use sodium bisulfite in water. Both will work. Just have to remember one of the formulas. And you make a cis diol. Okay. There's not an enantiomer because if they were both on a dash, they'd be the same compound. You could flip them and superimpose them. Okay. Now, sometimes when you use this reaction and you do the first step, which is the treatment with the osmium tetroxide, this is usually used in the presence of a compound called NMO, which has a long name, N-methyl morpholine and oxide. Okay. And what its role is to be a co-oxidant. The reason why you use this is osmium tetroxide is ridiculously expensive and it's highly toxic. So you want to use as little of the osmium tetroxide as possible, and in the presence of NMO, it works sort of like it's a catalyst. So it regenerates osmium tetroxide throughout the course of the reaction. So if you regenerate this, you don't need to have very much of it in the solution to make your product. So you don't need a mechanism for forming the cyclic osmate ester, and you don't need the mechanism for the dihydroxylation over here. You just need to know the steps. Are there any questions? All right, the last one, oh, actually this was 910. They put the syn hydroxylation in a separate section. So now we're moving on into oxidative cleavage, 911. So 9.11, which is called oxidative cleavage. Cleavage means to break. Okay. And so what you can do is you can take your alkene and you put it into ozone in the presence of DMS, and sometimes you'll see that zinc is involved. It doesn't have to be, but usually it's written in this way. Okay. And so this is a two-step reaction, but we're not going to go through all the details. Step one makes what's called an ozonide. And then step two is a reducing agent or a reduction. Okay, so the easiest way to do these reactions for alkenes is to cut your double bond in half. That's what it does. It separates the molecule by cutting essentially right at the double bond. And then count your carbons in the pieces. You have a 3-carbon piece, which you would redraw, and then on the end of the double bond, put an oxygen. And then do the same thing for the other part. 1, 2, 3, 4. 1, 2, 3, 4. Double bond oxygen. And then just make sure that if you used 7 carbons here, that you have 1, 2, 3, 4, 5, 6, 7 carbons in your product. And that's all you have to do. All right. So the next thing we're going to do is I'm just going to write up about 3 steps of things that you should look for when you're trying to predict the products of the addition reactions, and then we'll take a vote. Are there questions about oxidative cleavage? Okay. All right. So 912 is to predict products. These are all alkene addition products, or reactions, sorry. So the first thing you're going to do is you're going to ask yourself, what will be added across the pi bond? So what you need to do is, what are the groups, 1 on each carbon, that were added? When you look at reaction conditions, then you have to ask yourself, with respect to regioselectivity, if you're going to add by Markovnikov or anti-Markovnikov addition. And then also by your reaction conditions, you need to think about the stereospecificity. Do you get syn addition or anti-addition? And always ask yourself, will I make enantiomers? So at this point, we're at the end of what's going to be tested on Monday. So I have about 3 or 4 slides worth of reactions in which you have to either look at the reaction, look at the reactants, and propose a product. If you see the product and the conditions, you have to know what the alkene substrate was. If you see the reactant and the product, you need to know what the conditions were. We can do some of them, but they're not going to be particularly helpful in terms of helping you see where you stand in terms of, do I understand the material? If you still have to go back into your notes. You can't do that on Monday at the exam. So we have 2 questions. So I have 2 questions for you, or it's like A or B, but we're gonna have to say yes or no. So in the participants poll, moving on to 10 is a yes. Stay in 9 is a no. So if you could do that for me, please. Tell me what you think. Okay, so you're pretty much all wanting to stay in 9. Okay, so we can probably do, I mean, I don't think we're going to need an hour and 10 minutes in 9, but I think we'll stay in 9, and I'll show you a couple example problems and how to approach them, and then we'll move into 10. Okay. Okay. All right. So let me hide myself. Okay, so the first type of problem that you tend to see are going to be things that I'll ask you, what is the product of the following reaction? Okay. So, for example, if you have this alkene and you have the following reaction components. Okay. The question is, what do you make? Okay. So there are a few things that you need to think about when you approach this. Okay. So let's see, the first thing you need to be able to do is you need to be able to relate conditions, which are the given above and below the reaction arrows, to a specific kind of addition. Now, one thing you could do is you could make a list. So you could say we have hydrohalogenation, hydration, hydrogenation, halogenation, halohydrin formation, dihydroxylation, and oxidative cleavage. Okay, so those are the reactions from chapter 9. Okay. Now, sometimes the words in the question, or the words in these names, are very helpful. So in this case, it says hydrohalogenation. So you have to end up with a halogen on your substrate, but you don't have any halogens in your reaction conditions. So this doesn't make any sense. Halogenation doesn't make any sense. Halohydrin doesn't make any sense. Okay. Hydrogenation requires hydrogens. Now you do have hydrogens, but the hydrogenation conditions are hydrogen over a reactive metal. So that one comes out. Okay. Oxidative cleavage is just ozone in the DMS. So now you're kind of down to, do you make a diol or do you add water? Okay. So at this point, then it's going to be helpful if you can break those down into acid catalyzed, oxymercuration, demercuration, or hydroboration, okay, which is an oxidation. And the reason to go through this analysis is that if you know these names and you know what they mean and you know which reactions belong in them, now you have a boron and you have a hydroboration reaction. So this name is telling you you're using boron. Okay. Hydration is an HOH addition. So now it would just depend, do you remember which of these three is Markovnikov versus anti-Markovnikov? Hydroboration is anti-Markovnikov, which means your hydroxide will end up on that carbon. And that would be your product. Okay. What I would advise against is just memorizing what stuff looks like. And so what I mean by that is, don't just memorize, well, BH3 and THF makes an alcohol. You have to know what kind of alcohol. So it's better to be able to talk through your reactions with the right words in order to predict your product. Okay. Are there questions about that one? And then I'll give you one to practice.
Is this a good example of the type of questions that would be on the test?
Absolutely. So think about it this way, like if you, this is A, this is B, this is C. If you're given two, do you know the condition or do you know the third? So if I give you A and C, you have to be able to pick out B. If I give you B and C, you have to be able to identify A. A and B, you have to be able to identify C. There's word questions that you can use and have been done in the past. Like, what is the advantage of the oxymercuration demercuration reaction over acid catalyzed hydration? Because they both make the Markovnikov alcohol. But when you use acid catalyzed hydration, you have to consider racemization and rearrangement. You don't have to worry about that in the oxymercuration. So that's the synthetic advantage. So it may seem like, why do we have to know all these different things? Because there's a difference between making a primary alcohol, which would be out here, and a tertiary alcohol, which would have ended up in here. Because now this thing is a primary alcohol, which you could treat with a tosyl chloride to make a tosylate, and now do a substitution reaction and get something else out here on this primary carbon. But if you made a tertiary alcohol and you wanted to do substitution on that, you'd have to treat it with a strong acid to make a good leaving group. So these, you're being taught, and this is just the way organic chemistry is, you're being taught little bits and pieces that are eventually going to be used in a big synthesis. So the better you understand the pieces in multiple directions, the easier it's going to be. Okay. So I'm going to take these marks off unless there are questions specifically about this reaction. Okay. And I'm going to take this stuff off. because like checklists like this aren't going to be available on Monday unless you make them after you start the test. Okay. So you take a few minutes to work through that, and then we'll talk through it together. Okay, does anybody need more time? Okay. So when you look here, the important thing to recognize here is what this thing is. Okay, so this is the peroxy acid. And peroxy acids make epoxides. Okay, so without the second step listed, if it had just said MCPBA, you would have had to draw peroxide here. But because it's MCPBA and then a second step, which is the acid treatment, you're going to go all the way to the product of a dihydroxylation reaction. So dihydroxylation reactions have syn addition and anti-addition. Okay. Syn uses the osmium tetroxide. Anti uses the peroxy acid. Now, in this case, it's difficult to show the anti-addition because this isn't the pi bond isn't in the ring. So, and then because you would get some free rotation, as long as you would have a hydroxide here and a hydroxide here, you'd be fine. So that would be then the answer to that type of question. Okay. Questions? Okay, let's do another one where we switch up. Okay. what are the conditions for the following reaction? Okay. And the conditions mean, do you know what has to be above and below the reaction arrow? Okay. I'm gonna, while you work on that, I'm gonna get more coffee. Okay, does anybody need more time here? So in this reaction, you have two functional groups. You have an alkene, and then you have this nitrile. In the product, you retain the nitrile, but you've lost your double bond. Okay? But if you look at what's been added by drawing in the missing hydrogens, you've added a hydrogen to both sides. So this is a hydrogenation reaction, which requires hydrogen over some metal. Like I said, palladium, platinum, nickel, all correct. Okay. Questions? Okay, we'll do one more and then we'll just take any general questions and then we'll start 10 and then you know what, we're in really good shape. I'm really proud of us. Okay. Does anybody need more time on this one? Okay. So when you're doing these kinds of problems, sometimes it is really helpful to draw all the hydrogens that are on the vinylic carbons, both before and after the reaction. Okay. So that you can see when something is a repeat versus something that's new. Okay. So in these reaction conditions, you're adding HBr. Okay. But you have to be careful about where the HBr ends up. So this carbon here is tertiary. This carbon here is secondary. So since the bromine is adding to the less substituted carbon, it means that this is an anti-Markovnikov product. And you can only make the anti-Markovnikov product in hydrohalogenations if the HBr is in the presence of peroxide. Are there any questions about anything from 9 before we move on to 10?
I have a quick question.
Sure.
Can you just do a super quick review of syn addition and anti-addition now that we are sort of done with the...
Sure.
Yeah.
So the easiest way to show you that is to just take like a plain substrate and then just show it with respect to adding, like I said, the colored boxes. Because really, if the pi bond, for our purposes, if the pi bond is in a ring, these are much easier to classify. I shouldn't have erased all of those. Oh shoot. Okay, so so this is syn and this is anti. Okay, so let me write these out. So hydrohalogenation, hydration, hydrogenation, halogenation, halohydrin. I feel like I'm forgetting one. Dihydroxylation. Nope, that's right. And oxidative cleavage. Okay. So hydrohalogenation is, let me think real quick. If it was flat, let me just draw one real quick, and then I'll know. Okay. I don't think you would call this syn or anti, because the hydrogen is the tricky part of this reaction is the racemization because of the going through the planar sp2 carbocations. You get a top and bottom. So that isn't going to have a syn versus anti consideration. So hydration, let me think now. So racemization is going to happen, or could happen, with rearrangement for the acid catalyzed reaction. Let's see, I'm going to say anti for the oxymercuration. And then it's syn for hydroboration. Hydrogenation, that's syn. Halogenation is anti. Halohydrin is anti. Dihydroxylation, this is nothing. Dihydroxylation with the MCPBA and the acid, that makes a transdiol, so that's anti. And then the osmium tetroxide would be syn. So that would sort of be like, so you have some where it's specified, and then others where the consideration you would need would be rearrangements and racemization and making enantiomers. Did that answer your question? I think that was Karen.
Yeah, thank you.
Okay. So one of the things that you can do, like, and you could do it on Pinterest, you could just Google. There's websites like masterorganicchemistry.com. They have like study sheets where things are kind of all broken up, that if you want to, you could download those, print them, and try to help you. But in my opinion, like but this is just how I learn. I learn better by just repeatedly rewriting and practicing and rewriting and practicing and rewriting and practicing, not necessarily just learning it off of a piece of paper. Like, I have to do it in order to learn it. But if you want a guide or a place to start, that might be a good place to look for the Master Organic Chemistry class. Are there any other questions in 9? Okay, so I'm going to erase this, and then I'm going to find my notes for 10 because I didn't get those out yet. Okay, so 10 is addition reactions to alkynes. So we are going to be using triple bonds. The alkyne chapter is, in my opinion, is easier than the alkene chapter. So chapter 9 is probably the heaviest chapter in the book, in the course, because there's so many reactions and there's so many details. And those reactions are pretty well understood. Alkynes is a little bit a little bit different. Okay. So 10.1, we're just going to do some quick introduction to alkynes. So when we have an alkyne, this is acetylene. That's a common name. Okay. What you have are sp hybridized carbons. That portion of the molecule is linear with bond angles of 180 degrees. Okay. There are 2 pi bonds. So you have a total of 4 pi electrons. So there's 2 times as many pi electrons in a triple bond versus a double bond. So what that tends to mean is that reactions of alkynes are often similar to reactions of alkenes. They just happen twice. When you have your alkene, you have a lot of reactive pi density right in the middle of the compound. So this would be a partially positive side, and then you have all this high electron density. Okay. All right, in terms of naming, the ending changes to YNE. So if we look at a set before we do more work, this is pentane. One pentene. And the problem with the alkynes is you have to draw them with respect to the Vesper geometry, so you can't really zigzag through here. This would be one pentyne. Okay, now sometimes I try to draw mine with a break, but the computer programs don't. They're going to draw this one sigma bond super long and then put the pi bonds on either side. Can you hear that frog? Just ridiculous. Sounds like he's in my house. One here, a carbon here, a carbon here. It's still the same here. 1, 2, 3. Okay. The rules for naming alkynes are simply an extension of the rules for alkenes. So your parent chain must contain the alkyne. And things get a little bit weird if there's a double bond and a triple bond in there. They're called eneines, but we're not going to do nomenclature of those. It would just be a single functional group. Could have substituents like chlorines and other halogens and stuff like that, but okay. So in spite of the alkyl and halogen substituents, you want your pi bonds or your triple bond to have the lowest number possible. And again, you would give it a locant as a position of origination. So this triple bond would start on carbon 2. So in this case, we would have 2 methyls on 5 and a methyl on 6. So 5, 5, 6, trimethyl, 1 heptine. And again, remember that's the same as the new nomenclature way, trimethyl, hept, 1 ine. All right, in terms of some placement of the alkyne, the placement makes a difference. So the placement of this triple bond makes a difference. Okay, and what I mean by that, oh, sorry, I missed a couple things. Why would it be 1? Oh, it's not supposed to be 1. It's supposed to be 2. I'm getting distracted by frog croaks. Okay, so the placement of a triple bond makes a difference. And what I mean by that is this is called a terminal alkyne. This is called an internal alkyne. They differ in a couple ways. Only the terminal alkyne has an sp carbon to hydrogen stretch that's visible in the IR. Okay. Internal sp carbons, there's no sp carbon to hydrogen stretch. So you wouldn't see that feature in the IR. So if you drew the IR of these two different structures, okay, I have to make a slight change over here. Make it asymmetric. We didn't talk about how symmetry affects infrared, so we're just gonna make it asymmetric so we don't have to worry about that. Okay. So here's your 3000. Here's 3000. The internal would look like this. And then you'd have a feature for your triple bond. And this would be between, this is not to scale, 2300 and 2100. For the terminal, you would have something out here, then your sp3s, and then your triple bond. So this would be the triple bond stretch, carbon to hydrogen stretch. Okay, so they're different in the IR. Okay. The other way that they're different is, let me write this is again terminal, and this is internal. Terminals have a Markovnikov carbon and they have an anti-Markovnikov carbon, which means they have a more highly substituted carbon, which is primary. Wait, secondary. Your anti-Markovnikov carbon is primary. So you have a more highly substituted carbon and a less highly substituted carbon. in your internal alkyne, both of these are equally substituted. They're both secondary. So you can't distinguish Markovnikov versus anti-Markovnikov. The length of the chain doesn't matter. It doesn't matter that there's 4 carbons here and 3 carbons here. They're both secondary carbons, so they would both, you could say they're either both the Markovnikov carbons or neither of them are the Markovnikov carbons. You can't distinguish them when you do the synthetic reactions. So if you do a reaction on an internal alkyne that's supposed to follow Markovnikov addition, you're going to get a mixture of products because some will react on this carbon and some you'll see the reaction occurring more on this carbon. So there's a little bit, that's a big difference between the alkynes and the alkenes. Okay. Right. Questions so far before we talk about how we make them? I might sneeze here in a minute. Excuse me. Okay, so 10.4 is preparation of alkynes. Okay. So I'm going to break this up into 2 sections. First, just to refresh the preparation of an alkene. Okay. So when you have an alkene, you're going to use, primarily going to use alkyl halides, and you're going to do elimination reactions. And if you want to be sure that you only do elimination, you would use a strong base to force E2. E2 would require an 180 degrees dihedral angle. So that hydrogen would be the one involved in the proton abstraction to release the bromine, and then you would end up with your alkene. Okay, so this is all chapter 8. Okay. Now for alkynes, you can start in 2 different ways. This is called a dihalide. So they're both going to use alkyl dihalides. If the halogens are on a single carbon, so this carbon has 2 halogens on it, they're called geminal. So you have a geminal dihalide. And now you're going to write super strong. And you're going to end up with, oops, that's not right. This. Okay. Now, when you do this, it's a double elimination. So these 4 atoms would be involved in one elimination, these in the other. Okay, so it's an elimination reaction, E2 elimination happening twice. So 2 successive E2. Okay. Oops, wrong direction. Okay. The other thing you can do is you can use a dihalide where the halogens are on next door neighbors. Okay, so geminal, the two halogens are on one carbon. This, where they're next door, is called vicinal. They're neighbors. And you still have the same thing. You still have the bromine eliminating with this hydrogen and the bromine eliminating with this hydrogen. It's still a successive elimination reaction. And you still need to use a super strong base. And then you'll make your alkyne product. Okay. So before, I'm going to tell you what this super strong base is, but are there any questions so far? Okay. All right. So this is still going to be 10.4. Preparation of alkynes. Okay. All right. So strong bases like hydroxide, methoxide, and ethoxide are strong enough to make alkenes, but they're not strong enough to make alkynes. And these considerations are coming from the pKa of the reactions involved. Okay. So your super strong base, we're going to come back to the pKa after we do the reactions. But the super strong base is called an amide or an amide. Now, this is the conjugate base of ammonia. Okay, so it's like saying if ammonia would act as an acid, you would get amide. But you know that this equilibrium is dominated in this direction, which means this species, the amide, desperately wants a proton to make ammonia. Okay, so this is incredibly strong. Okay. Now you get it, the source is a salt, like sodium amide, lithium amide. You just have to get the amide into solution. And so what you would see is if you had a, let's just use a geminal dihalide. You want the elimination reaction to happen 2 times. So each amide itself can only cause one elimination. So you would need a 2-fold excess of sodium amide. And typically you use it in ammonia to make your product alkyne. Okay. So you need this in excess for both eliminations to occur, and they go by E2. Are there questions about the preparation of alkynes? Okay. So 10.5, now we're going to start reactions. There's fewer mechanisms required in this chapter than there were in chapter 9. So we're going to do reduction of alkynes. And the first thing we're going to do is we're going to see what would happen if we used the same conditions for reduction in an alkyne. Okay, so it adds by syn addition, but the reaction is so, the process is so reactive that you can't stop. So you can't stop here. So you end up making an alkane if you use hydrogen gas over platinum. So the problem with this is of making the alkane is there's really not a whole lot that you can do with an alkane. You can burn them, you can use them as solvents, but you've lost all your reactivity if you get all the way to the alkene. What we need to do is figure out how do we stop here at an alkene. We want to go from an alkyne to an alkene that will not, under further conditions, go to the alkane. Right. Now, when we have alkenes, though, we have cis alkenes and we have trans alkenes. So we have to have two different ways, one that will make cis and one that will make trans. Okay. So if you want to make a cis alkene, you start with your alkyne and you still use hydrogen gas, only you need a catalyst that's not quite as strong as the platinum. Okay, and it's called Lindlar's catalyst. And that's usually what is written underneath the arrow. And it's a combination of quinoline and palladium, barium sulfate. There's all sorts of stuff that goes into Lindlar's catalyst. It's essentially considered poisoned, because it makes it, the components of the Lindlar's catalyst poison the metal from going all the way, or from allowing the reaction to go all the way to an alkane. But you always stop at the cis product. And you don't go further to the alkane. Now, if instead you want a trans product or a trans alkene, then what you do is you take your substrate alkyne and you use a reactive metal. So you'd actually put like solid sodium or solid lithium into a very cold ammonia solution. These are usually below 0 degrees Celsius point. So they're very cold. The boiling point of ammonia is pretty low. So these are under cold conditions, and you make a trans alkene, and you don't go further to the alkane. So are there questions about making a cis or a trans alkene from an alkyne? Okay. So 10.6. Okay. This is hydrohalogenation. Which is addition of H and X. Now we're going to use a terminal alkyne to see the formation of the Markovnikov product. So when we use our terminal alkyne, again, this is the Markovnikov carbon. If you add one addition of HF, so for every one alkyne, you have one HX. You're going to get a vinyl halide. I'm sorry, a vinyl halide. Okay. If you do the same reaction, but you either say that you have excess HX or twofold HX, so twice as many HX molecules as alkynes, you go all the way to the alkane, but you end up with two bromines on a geminal carbon. So you end up with a geminal dihalide. So even though this adds by Markovnikov addition, the mechanism is not well understood. Okay. Because remember, in alkenes, with HX, they go through a carbocation intermediate. So in alkynes, you would have to go through then a vinyl carbocation. And there's no evidence for this. So the mechanism for the formation of the geminal dihalide is not well understood. You just have to pay attention to the stoichiometry to tell you when to stop. Are there questions about formation of a Markovnikov product for hydrohalogenation of alkynes? Okay. Just like in the alkene chapter, you can use HBr in the presence of peroxide to make the anti-Markovnikov product. And you can do the same thing for alkynes. Okay, so terminal alkyne. Now this is the anti-Markovnikov carbon. So in this case, if you put in one equivalent of HBr in the presence of peroxide, excuse me, then what you end up with is your bromine on the less highly substituted carbon. Now the trans product is not the only product you make. You will also see formation of the cis product. Okay, these have different polarities, and so they would be able to be separated. So they're geometric isomers. So this is the trans and this is the cis. And there's no mechanism details that you need for that reaction. Are there questions about this one? Okay, so in 10.7, sure. Yeah, okay. We're going to do the hydration reaction of the alkynes. Okay, now it's important to remember here that hydration is the addition of H and OH. The product of alkene hydration is an alcohol. The product of alkyne hydration is either a ketone or an aldehyde. Okay, so you're not going to make alcohols this time. Okay. Now, you can have an alkyne and do acid catalyzed hydration just with H3O+, but the reaction is really slow and not very effective. So you enhance, or you have the reaction go faster by using the acid in combination with a mercury salt. So if you have your product or your reactant alkyne and you put in sulfuric acid with water, so that's the acid catalyzed part. For an alkyne, you put in mercury sulfate. Okay. And we're going to go through some of the details, not of the first step, but of the second step. Okay. So initially, what you make is this structure. Okay, so because this is a Markovnikov addition, of hydrogen and hydroxide. So the hydroxide is going to go to the more highly substituted, or the Markovnikov carbon inside the alkyne, which is going to make this structure. Okay. This structure is called an enol. It's an alkene plus an alcohol. So it's an enol. But enols are not stable. It's very hard to isolate them. And they undergo a process that's called tautomerization. And I'll define that in just a minute. The product of the tautomerization is a ketone. When you have this internal enol, it's sort of like an initial product, but it doesn't stick around long. So the enol and the ketone, these two things are called tautomers. They're tautomers of one another. So tautomerization what that is an interconversion of constitutional isomers. So remember, constitutional isomers have the same molecular formula, they just have different connectivities between the atoms. So the reason to consider the enol is that the enol shows you that what you're adding initially across the pi bond is a hydrogen and a hydroxide. That's why it's called a hydration reaction, because you add H and OH. But then since that enol is not stable, you end up undergoing this interconversion and you end up making a ketone. That's good. Okay. So I'm going to stop here because the next part is the mechanism for this tautomerization, and I don't know if I have time to go all the way through it and finish that part of what I want to talk about. So we'll stop here, and then let me see. We have two more mechanisms in the or two more reactions or so in the alkyne. So we're in good shape to finish this up. So just in terms of where we are, 10 is reactions, 11 is reactions too, but not so many. And then chapter 12 sort of puts everything together. So in terms of new material, you really only have another part of 10 and then 11. So really like a chapter and a half left of new stuff, then we tie it all together. All right, are there any questions? I will be around, I'm actually going out of town this weekend, in spite of the rain. And I will have internet access, but I'm running. I'm going to go run with friends. So I won't be able to answer questions like as quickly as I normally try to, but I will be working while I'm not running. So just let me know if you need anything, and I will talk to you then on Monday. And we'll work a little bit on this, and then we'll review. And the exam, same thing as last time, the exam will be at 4 o'clock. If you have issues, let me know, and I'll work it out with you, okay?
I have a quick question.
Sure.
This is more about chapter 10 and 11 and 12. So on the final exam, will it be a focus on those chapters, but
No.
then also include stuff from other chapters?
It'll include stuff from other chapters. So the exam is, the final exam, there will be 4 groups of questions. So group 1 will be the first exam material for the most part. The second will be second exam material, third exam material, fourth exam material. And since it's only 50 questions, you can't divide that evenly by 4, but they're pretty evenly represented.
Okay, so there's not necessarily more of the...
No, and they're not weighted any more heavily than anything else. Everything is just 2 points apiece.
Okay, thank you.
Yep.
Dr. Walsh, I had a question.
Sure.
Is there any other websites that you would recommend for practice for exam theory?
Yeah, there's, let me share my screen. Let's see, because I've been looking for some new things. What am I doing? Okay. All right. So if you Michigan State Organic Chemistry Problems, they have a nice site, but you have to do a little bit of digging. But like if you look in here, functional group reactions, alkene transformations. So if you click on that, it's going to say you have these alkenes, and then you're going to react them under these conditions. Okay, so an alkene plus HCl, that's a hydrohalogenation reaction. And then what it's asking you to do is, do you want to do the reactant and have to identify the conditions to make a product? This is like the ABC type thing. The problem with this is that there are a couple things, like we didn't use potassium permanganate. So that's going to be a harder option. But if you got the one, and this one right here, this HOBR, that's a halohydrin formation. It's just written in a different way. So this is going like from an alkene to a chlorinated alkane. So that must be reagent A. And then this has 2 bromines in it. That must be reaction set B. And then you can check your answers and it'll tell you if you're right or wrong. So I do like this site, even though you have to find the questions that you want to answer. But they have all sorts of things. Like they have alkene transformations. Let's see, down here, let's see. Where do they have the substitution reactions? Nucleophilic reactions. You'd think they would just say, so this would work. You'd, like I said, you just have to do a few, like find a few things. Let's see, what else have I seen lately? That's any good. Master Organic Chemistry. Now, some of these things you have to log into. There's free stuff and then there's not so free stuff. But I don't think I'm a member here. Oh yeah, here's a catalog of study guides. And so like reagent learning, it looks like you have to purchase them. Summary sheets of reactions, information about spectroscopy, but some of the stuff on Master Organic Chemistry is free. There's good things on Khan Academy, and there's something called, oh God, what was it called? Clutch Prep. I did sign in for this one, and I went in and I selected my book as Klein, and then they have worksheets. So like in substitutions, you just would click start, and then it's videos about it, and then example problems. So, and Clutch is, from what I can tell, all free. And you can work through some of those, and then they show you reactions. I think what they're intended to do is that you practice the reaction, and then the person in the video describes it and sort of talks you through it. But those are the places I would start. And the nice thing about Clutch is you can do it right. You can specify which book you're using, and that would change a little bit of how useful it is, because some of the books are a little bit, you know, everybody has their own favorite book, so you'd have to pick the one that you're learning from. So, are there any other questions? All right, so y'all just have a good weekend, and you know, make sure you eat and sleep, and don't just spend all your time with this mess. Okay, it'll all work out. All right, well, I will see you guys on Monday, and if you need anything, just let me know. Have a good one. Thank you.
Thank you.
Yep, you're welcome.